Dear friends, this is part 3 of Fundamentals of Robot. In the previous video, we discussed about robot specifications. This is the continuation of that video. In this video, we are going to discuss about spatial resolution, control resolution, accuracy, repeatability, speed of motion. I am Dr.R. Professor, Department of Mechanical Engineering, RES College of Engineering, Dindigul. The precision of movement, that is decided by the spatial resolution. So the word spatial resolution means the smallest increment of movement into which the robot can divide its work volume. The work volume of the robot is divided into small increments, and one such increment is called as spatial resolution. So the entire volume is divided into number of increments, and one increment of that volume is what we are calling it as spatial resolution. The spatial resolution depends on control resolution and robot's mechanical inaccuracies. So then, what is control resolution? Control resolution is controller's ability to divide the total range of movement for a particular joint into individual increments that can be addressed by the controller. So the spatial resolution is a single increment in the volume, work volume, but control resolution is how a single range of movement in a particular axis. In a particular axis, the total range of movement is divided into individual increments, smaller increments, and these increments can be addressed by the controller. So these increments are called addressable points. I will explain with the simple analogy. If you are taking a steel rule, the steel rule's range is 30 centimeter. This 30 centimeter is divided into 300 increments. One increment is equal to 1 mm. So it is divided into 300 increments. So this 1 mm, that is the 2 marks in the steel rule, that is called as addressable points. So this is an analogy that I want to explain. So here, this is depending upon the controller's ability to divide the entire range into the addressable points. Here the number of increments that we can divide the entire range, that is equal to 2 power n, where n is the number of bits in the control memory. So when n increases, the number of increments is going to increase, and the addressable points are very closer, and it is going to reduce the control resolution. That means if the number of increments are more and more, then the distance between two addressable points is going to reduce. So you can get in a better way by seeing this example. A robot has one sliding joint with a full range of 1 meter. The control memory has a 12-bit storage capacity. So what is the resolution now? So the resolution is equal to 1 divided by 2 to the power of 12. That is equal to 1 by 4096. That is equal to 0.000244 meter. That is equal to 0.244 mm. So the resolution depends upon the bit capacity. The bit capacity increases, the resolution is going to, the control resolution is going to reduce. That is, the distance between the two addressable points is what we are calling it as control resolution. This is going to reduce, or it is going to be smaller and smaller when the number of bit storing capacity of the controller is getting increased. The total resolution for the entire robot can be obtained by summing each component resolution vectorially. So what is spatial resolution? How we can obtain the spatial resolution? By summing up the individual control resolution vectorially, we will get the spatial resolution. So simply remember, control resolution is the distance between two addressable points. The next term is accuracy. Accuracy refers to the robot's ability to position its wrist end at a desired target point within the work volume. So the accuracy depends is how the robot can position its wrist end at a particular point. This point is what we are calling it as a target point within the work volume. So this point is what we are calling it as a target point. The robot's ability to position its wrist end at a particular point. It depends upon how closely the robot can define the control points or addressable points. So if I want to go for a particular point, how well whether the point is an addressable point or not, or otherwise how closely I can go nearer to the addressable points, because the controller can ask the robot to go to a addressable point only. So the addressable point can only be reached, but I ask the robot to move to the target point. So there is a small difference between these two. That is, my wish is to reach the target point, but controller's ability is to move the robot to the addressable point only. So this difference between the target point and address point is what we are calling it as accuracy. I ask the robot to go to a particular point, but the controller can only reach to the addressable points. So if that is the case, what is the accuracy? The difference between the addressable point and the target point is called as accuracy. In the worst case, the target point would lie in the middle between the two addressable points. So the worst case, if you are considering, the target point is going to lie between the two addressable points. So here we are not considering the mechanical inaccuracies. So what is accuracy now? Accuracy is equal to 1/2 of control resolution. We are taking the worst case, the target point would lie between the two addressable points, and we are taking the accuracy as 1/2 of control resolution. So the control resolution is the distance between the two addressable points, and accuracy is half of the distance between the two addressable points, that is half of the control resolution. The very important thing is we are not considering the mechanical inaccuracies in this. So what are mechanical inaccuracies? So from the word itself we can understand what are mechanical inaccuracies. There are a number of mechanical elements. The robot's physical structure itself is a mechanical structure. We are having some power transmitting elements. So we are having links, we are having joints, we are having power transmitting devices. So the mechanical inaccuracies are the inaccuracies in the robot links, joint components, and its feedback measurement system. Where it comes from, where it arises? It arises due to the elastic deflection of the structural members, gear backlash, slackness in the pulley cards, leakage of hydraulic fluids, and other imperfections in the mechanical system. So all these things may lead to the mechanical inaccuracies. So it may be the physical structure, the elastic deflection in the physical structure, or otherwise any power transmitting device like a gear backlash, or it is having a power transmission like belt drive, the pulley slackness, or sorry, the belt slackness, or it is a hydraulic drive system, that is leakage of fluids. So all these things lead to imperfections, that is actually called as mechanical inaccuracies. These inaccuracies are worse for larger robots, since the components are larger here, and because of this the inaccuracies are larger in this case. And moreover, the mechanical inaccuracies depend on the amount of load handled, speed of the arm, the condition of the robot and others. For example, if the load is more, that may lead to more inaccuracy. And if the speed of the arm is very high, or the acceleration is more, that may lead to inaccuracies. Or if the condition of the robot is old, then that may lead to mechanical inaccuracies more and more. So we have already defined the accuracy. Accuracy is equal to 1/2 of control resolution without considering the mechanical inaccuracies. Now we are going to put the mechanical inaccuracies into the accuracy term. Remember, the moving arm to the addressable point is decided by controller's ability, that we already told. So the controller's ability, the arm is moved to a particular addressable point, that is decided by controller's ability. That is the number of bits of the controller, that is the controller's ability. But due to mechanical inaccuracies, the arm may not even reach the addressable point. So I ask the robot to move to the target point, but controller's ability is to place the robot arm in the addressable point. That itself is accuracy. That is the difference between that is accuracy. Now, if I want to place the arm in the, or the wrist in the addressable point, that itself is not possible because of this mechanical inaccuracies. That is going to affect the accuracy of the robot. So, when the arm is in a fully extended position, the mechanical inaccuracies are more, leading to poor accuracy. When the arm of the robot is closer to the base, the mechanical inaccuracies are less, leading to a better accuracy. That is, for example, if the arm is in the extended position, actually this is the target point I wish to go, I wish the robot arm to go, but the robot arm or the robot wrist is going to come to the addressable point, but because of these inaccuracies, mechanical inaccuracies, it may go here, or it may go here, or it may go there, or anywhere here. Okay, but in case if the arm is in a very fully extended position, it may go here. When the arm is closer to the base, it may come to this point, right? So, what is actually accuracy after including the term mechanical inaccuracies? So, accuracy is control resolution plus mechanical accuracy by 2. So, which one is the mechanical accuracy? This is mechanical inaccuracy or mechanical accuracy. You can see here, this is going to be a normal distribution curve. From one side it is going to be plus 3 sigma, and another side it is going to be minus 3 sigma. So it lies between plus 3 sigma to minus 3 sigma. Totally it is 6 sigma actually. So this mechanical accuracy is a normal distribution curve. So target point, my wish is to move the robot to the target point, but it has to go, according to controller's ability, it has to go to the addressable point, but it may go somewhere here. So I am taking this mechanical inaccuracies also into consideration in the accuracy term. So accuracy is equal to control resolution plus mechanical accuracy by 2. So this is what actually the control resolution is. So this is control resolution by 2. This 2 is equal to control resolution. The distance between here to here is control resolution. From the target point to this addressable point, that is control resolution. Therefore, here the mechanical accuracy from this point to this point. So, this distance is mechanical accuracy divided by 2 plus this distance, that is equal to control resolution divided by 2. So, totally accuracy is equal to control resolution divided by 2 up to this plus mechanical accuracy divided by 2. So, that is given here. Accuracy is equal to control resolution plus mechanical accuracy divided by 2. So, when mechanical inaccuracies are more and more, what will happen? This accuracy value is going to increase. Whenever the accuracy value is increasing, it means the accuracy is decreasing. It is the value is larger, but the real meaning is the accuracy gets reduced. Whenever the value of accuracy value is more and more, the accuracy gets reduced. So, when mechanical inaccuracies increases, that will affect the accuracy to a larger extent. The next one is repeatability of the robot. The repeatability refers to the ability of the robot to return to the programmed point in a number of times and commanded to do so. So, if the robot is asked to go to a particular point again and then again and again, then it has to reach the same point for all the times, but it will not happen. That is, this repeatability is going to refer the ability of the robot to return to the programmed point a number of times and commanded to do so. So, how well the robot can return to the programmed point, or how closer to the programmed point, that is what we are calling it as repeatability. So, for example, the robot is commanded to move to the point T, that is actually target point, but it can move only to P because of its accuracy limitation. This is actually the addressable point. So, it can move to P because of its accuracy limitation. But again I asked to return to the same point P. So, I am saying it for T, but it has to go back to P. But instead of P, it goes to R. Again, if I am asking the robot to go to point T, instead of R, it may go somewhere else. Right? So, there are number of cluster of points in between here. The robot may go. It may go here, it may go here, it may go here, it may go here, it may go here. It may go somewhere in between these 2 points. So, the repeatability is due to, so from the thing we can understand, the repeatability is due to mechanical errors. So, this is a normally distributed curve, as I already mentioned. This is plus 3 sigma, this is plus 3 sigma and this is minus 3 sigma. Here it is mentioned as plus R and minus R. This is plus 3 sigma and minus 3 sigma. So, the repeatability is in between these 2 points. So, what is the total repeatability? Plus 3 sigma, on the other side it is minus 3 sigma. Totally it is 6 sigma, R plus R minus 3 sigma. So, if you are considering a 3-dimensional space, it is only for one axis I am talking about. If you are considering about the 3-dimensional space, the repeatability errors will surround the program point, this point that is called as program point, and it looks like a sphere. So, and the radius of the sphere, that is what is considered as repeatability of the robot. So, here in one axis, for one axis it looks like a normal distribution curve, but if you are considering all the 3 axes, it is going to form a sphere, and the radius of the sphere is repeatability. So the robot manufacturer quotes the repeatability as plus or minus the radius value. So it is plus or minus r. Next is speed of motion. Speed with which the robot can manipulate the end effector. How fast the robot can manipulate its end effector is called as the speed of motion. The speed determines how quickly the robot can accomplish a task or accomplish a work cycle. So whenever the speed increases, the cycle time is going to reduce. But these are all the factors which affect the speed of motion. One is accuracy, second one is load, third one is distance to be moved. If you want more accuracy, or if the accuracy is increased, the speed of the robot is decreased as it needs more time to reduce the location errors. Sometimes if the speed of motion gets increased, it will reduce the accuracy. To avoid that, you have to reduce the speed of motion, because whenever the speed of motion increases, this may cause more mechanical inaccuracies, and that will reduce the accuracy of the robot. So if you want more accuracy, then the speed of the robot is decreased. Second one, when the load is higher, when the load is larger load, then the robot should be operated slowly to safely deal with the greater inertia and momentum. So when the object is larger and heavy, then obviously its inertia is going to be more, and the robot is going to carry that with a particular speed. Because of that, some momentum is also there. So because of this inertia and momentum, whenever we are handling heavier objects, obviously the speed of motion has to be reduced. And third one, because of acceleration and deceleration problems, again the speed of motion has to be controlled. One simple thing is, if you want to move to a single long distance, that will be done with a faster speed, and that will be carried out in a shorter time. But if you are taking smaller distances or short distances whose sum is equal to the long distance, it will take a longer time, otherwise the speed of motion is going to reduce. So the meaning is, for example, if you want to move 1 meter in a stretch, then it is the robot is going to move in a faster way and time is going to reduce. But if you want to move every 20 centimeter, it is instead of taking one stride for 1 meter, I am going for 20 meter, 20 meter, 20 meter like that. Then what will happen? Every time you have to accelerate and then decelerate, accelerate, decelerate. That will cause the speed of motion to reduce, as well as it will take more cycle time. So the comparison of all the specifications for all the four types of robo. This one is specification. This is a coordinate system, Cartesian coordinate system or Cartesian coordinate robo, cylindrical coordinate robo, polar coordinate robo, and jointed arm. So in the case of axis, all the robo we are considering are 3 axes. First, but Cartesian, it is going to be all the axes are going to be linear. In cylindrical, 1 rotational axis and 2 axis linear axis. Polar, we are having 2 rotational axes and 1 linear axis. Jointed arm, all are rotational axis. So the work envelope it is going to develop, it is going to be a rectangular work envelope, a cylindrical work envelope, spherical work envelope, and this is also almost spherical work envelope. So here when we are taking the work volume, this is going to be smaller and it is continuously increasing. Okay, so cylindrical is larger than the Cartesian, and polar is larger than cylindrical, and jointed arm is better than polar. And payload capacity, you can see in most it is 5 to 100 kg, 5 to 250 kg. Again the polar, the load carrying capacity gets reduced, it's 5 to 100 kg. And in jointed arm also it is a little bit more, 5 to 130 kg. The repeatability is so good. It is 0.015 to 0.1 mm, the Cartesian coordinate, because all the three axes are linear. The accuracy and repeatability, the mechanical rigidity is more, and because of that the repeatability is better in this case. But it is getting reduced. This 0.1 to 0.5 mm, this 0.5 to 1 mm. When the value increases, means the repeatability is poor, right? And in the jointed arm case, it is again 0.1 to 0.5 mm. The speed of motion, because in the Cartesian it is going to be fast, cylindrical medium, polar it is going to be very low, and the jointed arm again is faster. Again, one important thing is, though Cartesian and the jointed arm we are having a faster speed of motion, in the Cartesian coordinate system, in all the points actually the mechanical rigidity is going to be more. Even the robo is moving in an extended position or in a closer position. But in the jointed arm there is a different issue. When the arm is in the extended position, obviously the mechanical rigidity is going to reduce, and if you increase the speed at that time, it will increase more inaccuracies and the accuracy will fall down. Okay. The next one is need for a robo. So what are all the needs for introducing a robo in an industry? One is, as this is already discussed so many times, hazardous work environments. The environment is hazardous. Obviously there is no other choice. We have to procure a robo and we have to replace a human being. And the task is very difficult to handle by a human being. Then obviously a robot has to be used. Reduce the labor cost. If you want to do the operations repeatedly again and again and for 3 shifts, at the time the labor cost is more, then instead of labors we can replace the labors by a robot. And if you want to do the operations very quickly and if you want to reduce the cycle time, a robot can be introduced. Eliminate undesired jobs. Due to repeated jobs, accuracy may get reduced if you are using a human worker. So those things are avoided, and eliminate undesired jobs. So the inaccurate jobs or undesired jobs are eliminated. If you want to eliminate, then you have to go for a robot. And next one is, if you want to increase the productivity, then a robot can be introduced. Consistency and accuracy, and last one is increasing the product quality. In all these cases, a robot can be introduced in an industry and it can replace a human labor, or otherwise it may be a new environment. In that case, a robot cell can be formed by introducing a robot. So with this, we come to the end of the fundamentals of robot. So in this video, we have discussed about the spatial resolution, control resolution, accuracy, repeatability, and speed of motion. Thank you.